Hey all, welcome to another edition of Quarantine Science. We may have to retire the name because quarantine is kind of officially, unofficially over. Be working from home a few days a week and go in the office a couple of days a week. So may have to retire that name. We may gotta go to something like Sweatpants Science or who knows. Anyhow, I am down here working on this grandfather clock and realized there is something super fantastic about the grandfather clock, and that is how it keeps the time so accurate. And it's not so much the hands on the face or the mechanics overall that keep the time, and it's not the weight, but it's the pendulum. The pendulum had been the workhorse for over 300 years keeping time. Now, the fascinating part about this is that it really only prevents this weight from going down any further, and it only allows it, if you can see, a tick-tock motion. It only allows that gear to move so much. Now, what makes the pendulum such a great timekeeper? It's in the physics. The physics of it are actually fairly simple at small angles. Now, you get to larger angles that are closer to 1 radian, it gets a little hairy. In fact, you can add in certain percentages as you get closer and closer to 1 radian. And when you go above 180 degrees, or 90 degrees from that vertical, it gets really dicey. So the pendulum here, the only thing that determines how much time it takes to swing from one edge to the other, back to the other, is the length of this down rod down to the center of mass. And that's what we're going to be looking at today. Well, it's dinner time, so we're going to have to put this aside and go upstairs and eat. You're not joining me. Get your own food. So here we are. We are now after dinner. It was delicious. Thank you, Melanie. And we have my pendulum set up. Of course, you're looking at the string, and it goes all the way up to the top, and that's a 4-foot level. But the string is actually a plumb bob string from the local hardware store. And then I also have a measuring tape next to it, because if you remember, I was telling you that the period in which the pendulum takes to swing from one extreme out and back is only dependent on the length of the string. It's not really dependent on the mass, although you need to have enough mass on the end of the string, and we'll get into that, but you need to have enough mass on the end of that string to where you can overcome some of the drag or the wind resistant of the string. But aside from that, mostly independent of that. We do need a mass that's greater than the string itself. Just keep that in mind. But the equation for it, and I'll pop it up here next to the air vent. I'll pop it up, how about right here? There we go. We'll pop it up right here so you can see it. And G, we're going to use 32.2 feet per second square. And what that is just the force due to, or the acceleration due to gravity. Aside from that, you have the length of the string, which here in our case is 156 inches from the point at which it pivots to the center of mass in the plumb bob. All right, and let me get down and I'll show you the plumb bob and the measurement. There you go. There's the setup. And as you see, if you look real close, you'll notice that 156 sits a little bit high. We're going for about 1/3 the mass of the, or 1/3 the length of that plumb bob. If you remember from your algebra or geometry for a triangle, it was about roughly 1/3 the height of the triangle. This is just a triangle turned upside down, inverted triangle. So it went about 1/3 of the way, and it says 157, but I also have it hooked to the top of my beam up there. It's not really cantilevered because I do have a counterweight on it, so if it falls, hopefully it falls backwards and not on my head. That would hurt. So we have 156 inches. Now I went ahead and did the math for you. Turns out that based on our calculations, it's roughly 4 seconds. We're just going to go with the 4-second number, and we'll see how that goes. So we're going to do it first, and hopefully I won't get smacked in the head, but I always wanted to do that, but not with gravity. That hurt. Okay, smacked myself in the hand. Welcome to the floor. We're going to try this again. Now, here's the plump lob. I've already got it swinging. We'll just go ahead and start with a smaller degree. And remember, it's all based on the length, and we estimated that to be about 4 seconds per period. And what that is just how many seconds it takes to come back to this location, right? So we're going to start right here. Now I'm not going to start immediately. I'm going to let it swing a couple of times, and then there we go. And we'll just go up to 10. This will help smooth out some of the air. 10. 39.67. It's pretty close. I'd say that's within a margin of error. So you're saying, okay, well that's relatively small angle. That's a nice little trick. But what if we move it further out? Shoot, let's go all the way out here. I hope you can see that. And we're going to hit start right there. There's one. And that's 3.995. There's Jupiter again, because he just can't help it. So we are right on the money. If you figure margin of error, we're right there at 4 seconds, and even my calculation said 3.992. So we are dead on the money. What that's saying is it doesn't matter how far you displace it. I mean, you can displace it only this much and still get a 4-second.
And this is exactly why they use pendulums in clocks, because they're very integrated. They're very dependable for having the correct amount of time. It doesn't change. Now, the one thing that will slow this up as far as the amount, so we notice that there is some decay in the magnitude of swing. And that's due more to air friction. That's that drag that's occurring as the bob and the string cut through the air. And here we go. That's 8. And
there we go. Bam. Slightly over, but it's still pretty much 4 seconds. And that just shows you it's independent of how far we displace the weight. Now you say, well, wait a second. That's all fine and good, but what happens if we change the weight? You said it was independent of mass. Well, let's go ahead and do that. So this is a hefty plumb bob, and I'll kind of let it hit the floor here. That's heavy. So I'm hoping that this will replicate the center of mass, but we know that is nowhere near the mass of that solid brass. So we have something that's somewhat similar, and we'll do the same thing. Hopefully we won't get a lot of curl out of it, but we should be able to still tell when it reaches its maximum. And we're just going to let it go. We'll bring it out a little bit. And
there we go, we just hit start. And we're just going to keep going. That was 2, 3, 7. So we're going to speed this up. 8, 7, 8, 9. And as you can tell, we're a little bit
closer. Bam. Look at that, 39.77. Now, it is true that we did come in a little bit lower, and that may be a lot to do with we raised the center of gravity just slightly. There's not as much pulling on this string. There's not as much weight on the string, so the string kind of pulls up a little bit and it shrinks. So you do get a little bit of change in the length of string, but as you can tell, it's still not enough, and we just proved that it's independent of the mass. And this is why we use pendulums for 300 years to drive our clocks. 300. Went until the 1930s when we came up with quartz. Chew on that. We'll catch you next time.